Well, thanks to the conveners for inviting me, and hopefully this will answer all the questions that you have about chlorine in arc magmas. Now, the goal behind this talk and the goal behind this research is to address some of these issues. And it's a tie into what John said in a lot of ways, because what we're talking about is how do we deal with the fact that in thinking about these magma chambers, we need to deal with a variety of magmas existing throughout the crust, from basalts, andesites, dacite, all the way to rhyolites, and magmas that can be degassing at a variety of pressures. And the reason this became problematic is I'll talk to you a lot. We've talked about copper. We'll talk about it a little bit more. If we go to the existing data for chlorine, this is what we have. This is the actual plot from the Shinohara 89 paper, which I will eviscerate shortly. And what we're going to see is that actually we need a much more complex understanding of how chlorine behaves in terms of interacting with degassing magmas. So, again, to sort of break down the motivation here, we've heard about these different parts in several of the talks. First, we need to create an ore deposit. First, we need to create a magma that's enriched in a variety of trace elements. And by enriched here, I don't necessarily just mean copper. As we've heard, it might be fine to have a normal old copper magma. But certainly, we need to have significant amounts of chlorine. We need to have significant amounts of ore metals available. And then we have this question of sulfur, which I'll touch on briefly at the end. And a lot of the research that I've done has actually been dealing with this section, which is as we decompress and crystallize the magmas and induce volatile loss, I've spent a lot of time looking at the compatibility of not only the major elements, things like sodium, potassium, iron, and chlorine, but also the trace elements, the ore metals we're interested in, copper, gold, and molybdenum. And what we found for quite some time, a number of researchers have looked into this, and there are critical parameters. They're the ones we expect: temperature, pressure, FO2, and then critically things like the total amount of chlorine or the partitioning coefficient for chlorine and its related cations. And as I'll show you, although we can constrain this really well, again, our understanding of chlorine is relatively poor. And then, of course, we have this additional carry-on problem, which is once we actually exsolve the fluids from the magma, we then have to deal with how that supercritical fluid or intermediate density fluid then decompresses and turns into vapor plus or minus brine, and how those gas fluxes ultimately produce our ore deposit. So there's sort of two driving questions in my research that I've been looking at, and that is, again, one, what is the fraction of the iron, copper, gold, and molybdenum that is extracted from magmas when it exsolves a fluid? And one of the important points here, and I'll touch on it briefly, is actually I like to include iron in this because, as John and a couple others have pointed out, in addition to the copper that's bound up in sulfur in these systems, there's a massive amount of iron that's bound up in sulfur in the systems. So we actually need to be considering that when we think about these ID fluids, because it actually makes up a very significant portion of the chloride assemblage. And what I'll show you, as I'll talk through a little bit of the data that John touched on, which is that the extraction and transport of both copper and molybdenum depend primarily on salinity. I'll show you some of those relationships. We have a little bit of nudging here and there we can do. Gold will be important. I won't talk about it today because it's actually much more complicated. But if we want to understand modeling for these systems, we then need to be able to ask the more fundamental question, so which melts within our transcrustal system actually generate the fluids that can extract significant amounts of copper, gold, and molybdenum? And so how do these magmas and MBTs then change? And this, of course, is then asking actually the question, well, when does chlorine, sulfur, and iron, which is a major component and thus affects the phase relations, when do these actually degas from arc magmas? So John showed this briefly, and of course I just want to touch on the fact again that we're using sodium chloride water as a proxy here for the chloride package in these ID fluids. And the point is that if we start with something above about 1.5 kilobars, up here where it's roughly 2, as that ID fluid decompresses, we're going to result in a variety of different vapors and brines. We can have sort of magmatic or submagmatic vapors and brines. We can have hydrothermal vapors and brines. And of course, this is actually a three-dimensional surface, and in fact, ID fluids sort of slide along this surface and generate a lot of different vapors and brines. And in each of the cases, you can see here, over the range that I've talked about, we've got greater than 50% salt in the brines and less than 2% salts in the vapors. And so if we want to know the partitioning between this, not only do we need to know how metals are exchanged, but we actually really need to know what the input fluid density is, because this is what's going to control the tie line that's going to control our metal partitioning between the phases. So this is the plot that John showed, and I want to talk about a few features of it. This is work we recently published in American Mineralogist, and It's a compilation of data both from my recent experiments as well as a number of existing studies that shows how copper partitioning between a fluid and melt changes as a function of salinity. There's a couple of important features. One is, if we want to talk about old data, here's a number of experiments by Phil Candela and Holland from 1984. And the point here is that in some of the old compilations for these data, we're looking at quenched fluids. And one of the problems with a lot of the existing partitioning data is that the quenched fluids seem to not capture this additional partitioning we get from magmatic copper complexes. And so one of the things I'll have to convince you of is that if you're trying to look through and model with these sort of older partitioning data, you're actually missing an important feature, and that is the exponential relationship that exists for magmatic fluids between copper and chlorine. And that is to say that down here, this is 0.1% or sub 3%, we do have a somewhat linear relationship between copper and chlorine, but as we increase the salinity, we start exponentially increasing the amount of copper that we can put into that fluid. And this is an indication that we have these CuCl2 with sodium or potassium complexes existing in the fluid. Now, for a long time, people have argued that the presence of sulfur, and particularly reduced sulfur in these systems, plays an important role in the partitioning. So I did examine the sort of relative role here of having a lot of H2S. It will increase the partitioning, but as I'll show you in a second, the better evidence we have from the natural system is that this is not actually affecting the partitioning of copper. It is, in fact, chlorine. So as we pointed out, if we look at this as the chlorine partition coefficient, then of course down here in the 2 to 3 weight percent range, we're not going to be extracting copper very well. Something important to keep in mind is that if this D is 10 and we only have 10% fluid, 10 weight percent water in our melt, that means that we have a bulk D of 1, which is going to be very inefficient at extracting copper. At 10% water, we need to be more up in this range of 100 to have any hope of getting significant copper out of that melt. And in fact, we parameterized this as a function of the two types of complexes that we think exist and created this nice equation to predict the copper partition coefficient across any salinity. And I don't want to go into the details, but the point here is that in both cases, the primary control here is, of course, the salinity of the fluid. So to be able to model this, we need to be able to accurately predict the salinity of the fluid as it's exsolving. And this is another plot that John showed. Again, it's just touching on this point that as we create vapors and brines, the brine is going to continue to sequester copper as a function of its salinity. In the experiments, we do in fact get a one-to-one relationship between the partition coefficient for copper and the partition coefficient for chlorine between the vapors and brines. Again, here is the dashed line showing you the potential effect of H2S. This is, you can think of it as the maximum H2S you can have because these experiments would be already sulfide saturated at 800 degrees. And one of the challenges is that I don't like plotting it on here because I don't like people thinking that it's actually accurate. But if we were to look in the existing fluid inclusion data for how copper partitions between vapors and brines in inclusions in ore deposits, they plot way down here on the axis with up to 10 times more copper in the vapor than the brine. And I'm happy to discuss with anyone at any point later, but essentially there's been numerous experiments and later analysis of different inclusions that showed that those inclusions have been modified post-entrapment and do not represent the magmatic fluid composition. And the brief evidence I'll show you for that is that in the mole granite and Bajo, Seo and Heinrich went and looked at topaz-hosted inclusions that are not subject to this post-entrapment modification. And in fact, in 6 different assemblages in those deposits, this is the average and the 2 sigma error. They fall directly on top of the experimentally determined partitioning, showing one, not only is it chlorine that's controlling the partitioning between vapors and brines, they're dominated in the brines, but even more importantly, there is not a significant contribution of H2S that's affecting their partitioning, which means any sulfur that's present is present as SO2. And so we need to deal with that in terms of our evaluation of sulfur. Right, again. So, moving on to what I really want to spend time on, which is then how does chlorine, which is what we'll focus on today, we're going to be working later on things like sulfur and CO2, degas from these systems. And what I found is that the existing data for these volatile components is relatively unreliable and limited, in dominant part simply because of experimental limitations. And some of the critical questions that we were not able to ask is, when does chlorine degassing begin? Meaning not only how does the pressure affect things, but how does the melt composition and the total chlorine in the system affect things? These magmas don't come into the system as a haplogranite minimum melt with 2,000 ppm chlorine. And we know this because we have this whole understanding of the evolution of magmas throughout the crust. And then to break these down, we want to not only say, all right, well, what's the effect of pressure alone across the melts? How does the melt composition affect things independently? And then we can look at things like intermediate melts and sulfur and CO2 eventually. And then for chlorine, we have this additional problem because, as I'll show you, chlorine has several types of non-ideality in its partitioning behavior that pose problems. So here's the Shinohara data, which I promised to eviscerate. This is the plot that exists in the paper, which is in a very strange negative log scale. Here's what it looks like on some sort of sensible axis, showing this exponential increase in the partitioning of copper as a function of pressure. Now, surprisingly to me, if you go into the data tables, which are admittedly somewhat hard to read from most of the scans, you can pull apart the data that's making these anomalously errorless, perfectly constrained data points. And this is what it looks like if you plot it on a linear scale with the 2 sigma uncertainties on the data points, if you include all the data. And the point here is that 4 out of the 6 points have 2 sigmas greater than 100%. I can draw all kinds of curves through these that look nothing like this to define the the chlorine partitioning. And for reference, I've included just a few of our experiments and show you the relative uncertainties that we can get not only on single experiments but replicates in order to improve upon this method. And the critical problem here is that these experiments were done on haplogranite minimum melts with mass balance constraints. In addition, there's another feature you can sort of pull out, which is that although his data is hard to see it, there's actually a relationship between the total chloride in the aqueous fluid and the partition coefficient. We can see especially for these relatively low pressure runs, we get this steady increase in the partitioning as we increase the total chloride, which is an indication, again, that we have this non-Henrian partitioning behavior for chlorine. This is the case for some of the low pressure runs, but in fact the high pressure runs are actually chaotic, which is another indication that there's something going wrong in the experiments. And I'll show you that more here by putting it on this plot that I'm going to sort of take you through to show you the data that I've been collecting. So here we have the chlorine partition coefficient as a function of the melt composition and pressure. Here's dechlorine, fluid over melt, and here's the pressure. And then I've contoured the various data points here on these different bars for the total chloride that's present in that fluid so that we can look at this effect of the total chlorine. And here's the averages for the Shinohara data along with the individual data points. And what you'll see is that for the low pressure runs, we do have this nice relationship where the low salinity partitioning is at, the low salinity experiments are at a low partition coefficient, and then they steadily increase up through the system. However, the 4 and 6, and to some degree, so the 4 and 5 and 6 kilobar runs, if we look at those things, it's actually a very chaotic relationship between the different salinity experiments, indicating that they are not actually accurately sampling the effect of this non-ideal behavior. So there's something else wrong with the experiment design. And this is actually shown that it exists in a variety of experiments. We can look at experiments by Jim Webster, Shinohara, there's Singular and Carroll experiments that are listed, and all of these are showing this very strong relationship between the absolute chlorine concentration and the partition coefficient, and also the non-ideal behavior. And there's 2 reasons we have non-ideal behavior. One is this relationship between the concentration of chlorine in the melt and the partition coefficient. And the other, as I'll show you in a second, is that as we approach the very low pressure end of the system, we have this additional complication of vapors and brines. And that vapor-brine unmixing relationship actually also impacts the non-ideal behavior of chlorine in the partitioning. So what we've done is come up with integrating several aspects of other experiments we've done into the chlorine partitioning experiments to improve them upon these old mass balance designs. So the first is, how can we accurately measure the dechlorine in realistic melts? Meaning that we want to be able to get rid of this unreliable data, and the primary way we're doing that is by trapping synthetic fluid inclusions using in situ fracturing. And what that means is that the experiment actually contains a quartz core. The experiment's allowed to equilibrate for several days so that the chlorine can fully partition into the melt. We know that it can take 24 or even 48 hours for chlorine to equilibrate and silicate melts in these runs. And so by trapping the fluids after that equilibration, we ensure we're getting an equilibrium fluid and an equilibrium melt. In addition, we're measuring the chlorine in both phases directly. One, this prevents problems with mass balance in terms of the overall uncertainty, but even more importantly, it actually allows for non-liquidous experiments. If you want to do mass balance experiments and you have 50% crystal, you have a big problem in trying to evaluate your mass balance for chlorine or sulfur. And so we can do experiments on dacites and hopefully even into andesites. The other thing is that we have a few new types of experimental vessels at Bristol, one of which has been, for a few runs, successfully run up to 400 MPa and 850 C. And so this again is letting us access both rhyolites and dacites from not only the shallow but into the mid-crust, and allows us to then look at some of the relationships from much more realistic melts. So this then is a compilation not only of a lot of existing data, but of all the new data points, and I'll show you the relationships here by showing you these different colored fields. And the importance here is that the field has been colored, again, to show you this relationship between how the sort of range of values that we get as we sample different salinity fluids, but then increase the pressure and look at the partitioning. So here what you can see in this orange field is if we go to 2 and 3 kilobars, here we have nearly haplogram at minimum melts. They're a little, even at 2 and 3 kilobars, they're already a bit below the Shinohara data. And what you'll notice is then as we decrease the pressure, we get a very strong decrease in the partition coefficient for chlorine into the fluids. But one of the dominant reasons this happens is that we're actually creating vapors and brines, which means that the salinity of the vapor that we can generate is decreasing very rapidly. And you can actually see this by looking here. These are the brine partition coefficients relative to the melt, which are in fact very high. The problem with the existing data is that this has been conflated. So often the brine and the vapor will be put back together to create some partition coefficient, but in fact the partition coefficient thermodynamically is controlled independently by the brine and the vapor. And I can convince you of that by pointing out that if this is the vapor and this is the brine, I can't give you a partition coefficient for those mixture because I can create any partition coefficient I want between 1 and 100 by having different mixtures of vapor and brine, despite the fact that the chlorine in the 3 phases never changes throughout any of those compositions. So thermodynamically, we must treat these as separate phases, which means we need to do experiments where we measure them directly. Now, for the rhyolite, I'm missing a data point here, which is unfortunate because it exploded. But I'll show you some of the other ones that didn't for the dacites to show you another important feature. And that is that if we look at the dacites, already you can see we've dropped by another half order of magnitude. Now we're down here an order of magnitude below where the Shinohara data is, again, between 2 and 3 kilobars. These are for dacites, and what you see here is this is 2%, 4%, and 8% salt. So we are having a very significant impact of the chlorine in the fluid on the absolute partitioning. But again, we see this negative relationship dropping down, and that's because, again, for these dacites, we are generating both vapors and brines once we get down into this sort of 100 MPa range. Again, here's the brine partition coefficient, which is just showing you again that if we want to deal with these fluids, we need to be measuring it directly and modeling the creation of both fluids. But what's very interesting is not only are we an order of magnitude below this haplogram at minimum melts, but in fact, by doing experiments at 300 and 400 MPa and measuring them directly, the partition coefficient actually flatlines rather than increases steadily as we increase pressure. Now we have plans to do not only some experiments up here, and Bob's going to be doing experiments at even higher pressure to evaluate whether this continues, but if it's the case, then it has a significant impact on this idea that we have very high partitioning for chlorine in the very deep crust. Because, of course, even dacites at 400 MPa is going to be a relatively high-pressure dacite in the system, and in fact, we'll have even less evolved melts as we look in a minute. And so if we want to deal with those less evolved melts, there's a little bit of data. We're working to improve upon this, but Zoltan Zayats and some others have done a few partitioning experiments for chlorine into andesites. And what you can see here is this is the range for the chlorine in andesites for most natural systems between about 0 to about 2,000 ppm. He evaluated all the way up to a weight percent. But the point here is that despite that huge range of chlorine, the D actually goes between a little over 1 to a little over 2. And the point here is that if we plot that here on our diagram, this is where our andesites are at 2 kilobars. Again, we hope to improve this by using these experiments to examine a wider pressure range. But as I'll show you in a minute, we're not going to be getting much chlorine out of an andesite if the D for chlorine is 2. And I'll remind you again that this is the D between the fluid melt. So again, if we have 10% water, a D of 2 means a bulk D of 0.2, which means that we are not stripping chlorine out of an andesite. I'll touch briefly on this. There's some limited data for basalts over this pressure range. There are some problems with some of these experiments. This is some by Aletti, where he did look at the low pressure end. There's some others by Jim Webster and Stelling from 2008. And so I plot these here. This is just to show you that this is a rough estimate of the field for basalts. And the point here is that we're down at the andesite levels or even lower. Once again, we're not going to be extracting chlorine from degassing from basalt. It's simply too compatible in the magma. And so one of the things that I then did is I thought about doing the type of thing that John talked about. This is showing you sort of a stepwise approach to the type of modeling he discussed, which is to look at various ways in which we can take an andesite at depth and allow it to crystallize and differentiate and degas. And then evaluate, based on what we sort of know about chlorine already, how this impacts the ability to get chlorine out of a magma. And I'll show you just some rough cases to give you an idea of what we intend to do with this partitioning data as we short up. So one is the idea of allowing for open system degassing, meaning bringing an andesite to very shallow levels while allowing the fluid to be removed from the magma. And the short version of this, I can tell you, is that you're not going to get much chlorine out of the melt. And the reason for that should be relatively obvious. We have a very low partition coefficient, and we're dissolving a lot of water as we ascend towards the surface. So here's the melt fraction, and the point here is that because the D is relatively low, this is the MVP salinity, we can start off relatively high, but because we have a low partition coefficient, as we dissolve more and more water and ascend towards the surface, we're going to be not extracting chlorine from the magma. If instead we think about the case of, for example, second boiling, this is a case that's commonly considered in older models for porphyry copper deposits, we can in fact allow for some copper extraction during a period of second boiling if we have the right magma composition. And that's just to say that, of course, if we have a high enough MVP salinity, if we have high enough chlorine, then initially we will strip some of the chlorine out of the melt, but we can reach a steady state where every time we crystallize a little bit, the chlorine stays relatively high and partitions into the fluid. If instead we allow for decompression with minimal crystallization, meaning we're actually just bringing an andesite straight up and allowing decompression to degas, this is terrible for the formation of porphyry copper deposits because, as I pointed out, despite not knowing what the copper partition coefficient is, the chlorine partition coefficient is very low, and so by degassing large amounts of water while not allowing for chlorine enrichment due to crystallization, we're just going to be stripping very chlorine-poor water out of the magma the whole way to the surface. And so I bring up these cases because, in fact, if we want to understand what's going on in a transcrustal mush, we actually need to sort of integrate between these different options and put them together to evaluate how a staged decompression with stalled crystallization can create very copper-enriched fluids. And so I won't spend a lot of time because I'll run out of time talking about the model, but the point here is that we want to bring an andesite in, allow it to crystallize for a little bit at, say, 500 MPa, then allow it to crystallize a little bit at 400 MPa, and at each one of those things extract some of the fluid. And so here you've got 500, 400, 300, 200, 100. And the end result of this is that because we now have the ability to evaluate how chlorine partitions between rhyolites, dacites, and andesites, we can take these three things and put them together on this plot and say, this is the case, so the limiting case where we have an andesite, and this is essentially what's happening in that model, right? We have an andesite that's degassing, it's not crystallizing significantly, so it's staying an andesite, and essentially it's staying down here in this 2 range with a tiny uptick at the very, very last gasp, but there's no point at which we're extracting any significant copper. So we want to limit the degree to which the andesites are actually degassing before differentiating. Now, another option would be to say that we do almost all the differentiation to a dacite, for example, within the deep crust. And that will cause a significant increase in the partition coefficient because we've gone from andesite to dacite. But we have not actually allowed for significant water removal. And so, in fact, what happens, at least in the models we've run so far, is we take copper out at sort of a steady state. And so here's the partition coefficient. We're staying somewhere around 10, which is a sort of neutral amount for getting chlorine out. And as I could show you, if we take that and look at the copper partition, it means we're staying in that sort of low linear end of copper extraction, which may be sufficient. But in fact, what this shows us is if we hybridize these and allow for some ascent and differentiate, some ascent of the andesite to sort of 300, 400 MPa, and then creation of a dacite through differentiation, we will be in the stage where we have a much more significant amount of water extraction due to loss of water not only from decompression but also crystallization, where we have a lower solubility, and this will in fact push the chlorine partition coefficient up here into higher levels, and this is where we can access that exponential increase in copper partitioning due to these magmatic copper chloride complexes. Now, this is by no way a definitive thing. We want to improve not only the modeling, but our understanding of the partition coefficients for chlorine. But this is the type of thing that we want to do to be able to use these to more effectively evaluate how copper partitions in these different scenarios for the transcrustal magma system. The final thing, of course, is that I've cut all these models off down here between 100 and 200 MPa, and that's because we then need to consider what happens if we form brines, whether they form out of the magma chamber in equilibrium with the magma, and evaluate those scenarios differently, which we are going to be able to do now that we have the vapors and brines, but I don't want to speculate at this point. So if we go back to our two questions, if we want to understand how chlorine partitions as a function of total chloride, we now have experiments from 50 MPa up to 400 MPa, soon to be 600 and beyond, using synthetic fluid inclusions that give us a direct measure of the chlorine partitioning that is a significant improvement over old mass balance models. And what we see, and not only are we directly measuring, but of course we can look at realistic melts. We don't have phonolites and haplogranite minimums transiting the entire crust. And what we can see so far is an indication that not only do we have a lower partitioning for chlorine, much more complicated partitioning of fluids, but the potential for a plateau in dechlorine rather than a strong increase in pressure, which is much more consistent with what we see in terms of the melt inclusions for magma chambers, for volcanic systems. And then what we want to be working on is the progression from andesite to dacite to rhyolite. Again, here we can see melt composition has a very strong effect, and once we complete the project, we should be able to evaluate this across the board to have melt and pressure independently constrained. And again, here we're working on ways to get at those less evolved melts. And this just covers sort of what I was saying, that D changes with pressure up to about 300 MPa and then flatlines. Melt composition has a very strong effect that's been critically under-evaluated by the existing experiments. And combining them will then allow us to develop this broader relationship between pressure, salinity, and melt composition for the different models that people will want to run for magmatic differentiation. And then going forward, we have designs to go into andesite. Obviously, this process can be done for CO2 and sulfur. It complicates the fluid phase relations significantly, which is why we're starting with just chlorine. Because obviously, as we've pointed out, the coupled exsolution of sulfur and chlorine and CO2 is going to be a much more complicated process. And ultimately then, we want to be able to take those nice new partition coefficient equations and plug them into these models to track the ore metals along with the volatile species. So, thank you.
Thanks very much, Brian. We've got time for a couple of quick questions. You, Jamie, first then.
Thanks, Brian. That's good. Could you comment a little bit more on sulfur speciation of copper? Because you kind of alluded to it, and
Yep.
I think you sort of said that you thought it probably wasn't important, but on the experimental data you showed that it did increase the partitioning.
Yeah, so
it's an element you might expect to, and people have suggested it many times, that it can be sulfur species complex.
So it absolutely is, but there's two things I'll say. Let me get the junk off this. So there's two possibilities for how reduced sulfur can impact the partitioning. So essentially what I have here is these experiments that you see in the square boxes are experiments that have a significant amount of sulfur, but all the sulfur is present as SO2. So they're nickel-nickel oxide plus 2. And these boxes, virtually all of the sulfur is present as H2S. So the ratios are here, H2S to SO2. And certainly if you had a fluid that had all of its sulfur present as H2S, there's two possibilities. So one that's been suggested is the presence of CuHS2, meaning a purely sulfur HS complexed copper. However, what Zoltan looked at in some of his experiments is that the stability of this complex without any chlorine, without any substantive chlorine present, is radically lower, hundreds of times lower than the stability of any other complexes. And so it's something like 6 ppm is the limit at between 800 and 1,000 degrees for that sulfur-only complex for copper. Now, I mentioned for gold, I didn't want to talk about it because in fact it looks like this sort of thing might be important for gold rather than copper. But for copper, we have a mixed species, which is the CuClHs, and that does contribute to this bump in the copper by about a factor of 2 at the maximum amount of H2S, meaning chalcopyrite saturated fluids. So certainly it is the case from an experimental standpoint, they do increase the partitioning. My argument, however, is that if we look at the fluids from the actual ore deposits, if those fluids had copper that was partitioning because of a significant amount of H2S in the fluid, they should fall somewhere significantly off this chloride-only line towards this H2S-rich line in terms of the partitioning. And in fact, the fluids that we see that have significant amounts of sulfur, where they haven't been readjusted, fall on the line that's determined by SO2-dominated or sulfur-free, sulfur-poor partitioning.
I guess the key question you want to know is really what the sulfur speciation is at the point of separation of the fluid from the melt.
Right, and so in addition to the experiments which we can and are planning to do on sulfur between vapor brine, the ideal thing, and our plans in the works, is to try to do spectroscopically looking at complexation and sulfur speciation in those. And it's basically a race between reaction cells and HDACs to get at those conditions.
One quick question behind you.
Yeah, you showed quite clearly that basalt is much lower than rhyolite, but you didn't say why.
So the general wisdom is that the primary control on the melt effect for chlorine is the melt polymerization, because chlorine is affected to the oxygen network within the silicate melt. So the idea being that because basalts are incredibly depolymerized, they show very, very high solubilities for NaCl in the melt itself. In fact, some of the extrapolation in that data is weight percent NaCl dissolved into melts at high pressure. And so as we march through our melt differentiation and create more polymerization, the chlorine gets more and more unhappy, substituting in for oxygen in the melt structure. And so that's driving this incompatibility as we go up.
Great. Thanks very much, Brian.
Yeah.